Can you hear me?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
I sent you a note last time. I taught a little bit wrong, but that I'm going to clarify. Okay, but before that, let us talk about continuity between topological spaces. So, look at page 134. Okay, theorem 3.3. Look here, I have 4 equivalent conditions. So you have a function between two topological spaces. These are topological spaces. And I have given the conditions on equivalent conditions. Equivalent conditions for f to be continuous. That means the continuous on whole x. That means continuous at each point. Now look here. I have given 3 equivalent conditions B, C, D. B is inverse image of an open set is open. D is inverse image of closed set is closed. And C is this. FA bar is this. For all subset of X. Okay, proof. You can see there will be similar proof, except now I want to explain them. Look, sequential characterization of continuity is missing. Sequential characterization is missing. Now look, previous result for metric space, from B to C, it didn't go straight. From B to C, you went in between, there was sequential characterization. So we went from B to sequential characterization to C. Here you will have to prove directly B implies C. But proof is easy, that you should read. Okay. So sequential characterization in general not possible. Okay. In general topological spaces. Okay. Sequential characterization is not possible. It is not actually problem with the function or topology or topological spaces. This is actually problem with the sequential characterization. Sequence is inadequate to characterize many things. Okay, here I have not talked about it. So here sometimes that I told you that when you have something inadequate, so sequence in general is inadequate to characterize many things. Okay. That reason, one reason is basically is cardinality. Look, any sequence, range of a sequences has to be countable, which is actually small size, which basically small according to set size. Now, thing is that I'm just mentioning that is we can remove this inadequateness by removing. We can remove this inadequateness by defining Nate. It's a generalization of sequence that I will teach you next semester. Okay. So with Nate we can do it, and that Nate is a very useful and simple tool. So that so first you see that theorem 3.3 again, except B implies C, other proofs are similar what you have done before for metric space. Okay, so I am not going to repeat it, you should read it. But about sequential characterization, okay, that also I made a comment remark on that. That in the previous result there are 5 equivalent conditions, but in our theorem there is one less. Sequential characterization is missing. In fact, for a continuous map between two general topological spaces, we may not have sequential characterization. In the following example, I explain the anomaly. Now look, counter example. There is why it is wrong, and that sequence initially will be countable. That may be countable infinite. So it may not be finite. So that you are taking X uncountable set that I defined, X uncountable, and this tau topology is co-countable. Okay, co-countable. Now look here, tau is X phi union A subset of X such that X minus A is at most countable. That is either finite or countable infinite, is at most countable. This is the topology for co-countable. Okay, so closed sets will be what? Closed sets, tau closed sets basically. Tau closed sets, sorry. Its complement will be what? X phi, okay, and all at most countable sets. Most countable subsets of X. That means closed sets are this. Family of closed sets, that X phi intercept. All finite subsets of X and all countably infinite, countably infinite subsets of X. Okay. Now look at what will be the convergent sequences. Now look, what are the convergent sequences? Convergent sequences, whatever argument I gave, this is correct, except that you'll have to take co-countable topology and X uncountable. Convergent sequences in X. So take, suppose Xn goes to X. Xn is a convergent sequence. Okay. Then you take A equal to this, such that those Xn, such that Xn not equal to X. Now A is at most countable because sequence range is at most countable. To take when this, they may not be distinct as a set. As a set, it is at most countable, that is finite or countable infinite. But here I do not know that A is at most countable. So that X minus A is open because its complement is A, which is this. So there its complement of this set is A, and A is at most countable, so it is open. And look, A is all those so that Xn not equal to X, so that X belongs to X minus A. Now X belongs to X minus A, and X minus A is an open set containing X. So by the definition of the convergence of sequence, there exists N naught. There exists N naught belongs to N. Look at the top of the page 136, that there exists Xn. So there exists Xn such that Xn belongs to X minus A for all N greater than equal to N naught. Actually, I have explained more than what is required, but Xn, look, this means that I commented actually the below star, you see them. So xn, it means xn doesn't belong to a. Xn doesn't belong to a means xn equal to x. That means xn doesn't belong to a for all n greater than equal to n naught. That precisely means xn doesn't belong to a, means xn equal to x. So you get xn equal to x for all n greater than equal to n naught. That means it is eventually constant. And after n naught, everybody will have to be x. I am not saying below n naught it may be equal to x, may not, but that I am not concerned about it. So that I have proved every convergent sequence in x tau where x is uncountable. And why I am saying uncountable? Because you on a countable set, if you take co-countable topology, it will be discrete. Okay, that also will be true. But here I need for some other reason. So every convergent sequence where x is uncountable and tau is co-countable topology is eventually constant. Okay, is eventually constant. So that here every convergent sequence is is eventually constant. Now to take the special case, so that I am saying why I am explaining in this page that why sequential characterization is not possible. Now take x equal to r. On R you are giving, R is an uncountable set. R you are giving co-countable topology. Now y equal to, you take this. And what will be the closure of this? First of all, closure will have to be a closed set containing y, and which is the smallest closed set. Now look, here I claimed only closed set containing y is R, because closed set I told you that you have here closed set R, y, and at most countable subsets of R. So it has, these are the closed sets. Okay, so of course phi is out of question. This is also out of question because look, y is uncountable. So if you think of any closed set containing y, that has to be uncountable. But among these closed sets, only R is uncountable. So that y bar has to be contained in R. But R is the only closed set containing y. So y bar equal to actually R. Okay, right? Now any convergent sequence. Now look, if like y sequential characterization of closure point, first of all, is not possible. Look, if you take x, now 0 belongs to y bar equal to R. Now if you take a sequence xn in y such that xn goes to 0, but xn is in y, means xn's are all non-zeros, and eventually they are constant. That means xn will have to be equal to x for some n not such that n naught and n greater than equal to n naught. But that means it has to be 0, but it is not 0. So that here 0 is a closure point in particular case, but there is no sequence coming from y which converts to 0. Okay, right. So closure point is not possible. That is, sequential characterization of closure point is not possible. Now look, that I am saying sequential characterization of continuity here in this case is not possible. Okay, so I have, look what I have done here. Here I have taken R tau. This tau is co-countable topology. Co-countable topology. And here we are taking R sigma. Sigma is discrete topology. And you are taking the map identity. That means x is going to x. Okay. Now look, here I send every convergent sequence to convergent sequence because I have already, why I proved that. I proved a convergent sequence here will have to be eventually constant. If xn goes to x, then xn equal to x eventually. That is after a while. That means its image will be also this here. But in a discrete matrix space, every eventually constant sequence obviously, in fact, any topological space, every eventually constant sequence is convergent. So it convergent. It is also convergent here. Okay, right? Because I have made the convergent sequence only eventually constant here. So its image will be eventually constant here. Eventually constant sequence always converges. So it is converging. So that I have that I sends convergent sequences. I sends convergent sequences to convergent sequences. Now look, why this is not continuous. Here discrete topology, so every subset is open. So in particular, this is open. Okay. So I inverse 0, 1. I is identity map, this is 0, 1. Look, by the result equivalent condition, inverse image of an open set is open. That condition B. So it should be open in this. If this is open, it should be open in R tau. It is co-countable topology. That means its complement should be countable, at most countable, but its complement is uncountable because its complement is this, which is uncountable. So this is not open. So that means I is not continuous. समझ गया? Not continuous. Okay. Well, again, I am telling you, I am just giving you the example on that. But next semester, I will teach you more in detail. By that time, I think you yourself will understand much better. Okay, right? So that here I wrote in page 137 for the last year that I won't teach it, but this time I will teach you topology. Okay, so that here I'm going. It is true that among all types, page 137, all types of topological spaces, probably the metric spaces are nicest. But in life, that's the thing. We do not land up with only nice things. Actually, the problem is not with topological spaces, this is with the sequences. In order to understand the inadequacies of the sequences in handling the topological concept properly, you need to wait for one more semester. The next semester, you will take a course on topology. That I will teach this. We end this section with the result on the oscillation. So I have taught you topology, but whenever only open sets are involved, you can do. You don't need to bother about metric space of them. You can, this semester you can use metric space if you feel comfortable. But when only open sets, closed sets are concerned, I am telling you that won't help you, whether you take metric space or topological space. Now, I don't know whether you have been taught in undergraduate, that is oscillation of a function. In fact, even for this, suppose you have this function and x belongs to R, then what is oscillation? Oscillation of f at x. This notation is basically this. Basically omega or W2. Omega WF at x oscillation. Why we want to consider oscillation? Because oscillation is directly related to continuity. Continuity of f at x. This can define in general for between any two topological spaces. So in order to do this, I have defined here F sigma set and G delta set. Look, this is generalization of closed sets. F sigma set means that I have given you any countable union. It is countable, I mean finite or countable infinite. Countable union of closed sets. Look, finite union of closed sets is always closed. So that when I give this definition, that means actually you are taking countable infinite union. Here, any countable intersection of open sets. You are taking, of course, the topological space. Look, here I am only dealing with closed set, open set, so it's enough to have a topological space. I do not need any metric space in particular. So any countable union of closed sets. Why I am doing it? Because countable, if you have infinitely many countable infinite, that closed set need not be closed. But here I am giving that is F sigma set. Okay, similarly here, like any countable intersection of open set. Like here, if you take this special case, Q is not closed in R because its closure is R. Q is not closed, but Q is countable union of the Q. I can write Q is countable. So this is a countable union of the points, and each point is closed in a metric space. So Q is an F sigma set. Here I should tell you something. F apparently is coming is a consonant. Why it is an? Actually, it depends on the pronunciation, the sound. F. For F, A is coming. That's why it is an. It is an F sigma set. Okay. Right. Similarly here, look, to take even 0. Look, 0. 0 is not an open set in the same space. But 0 I can write, look here, this way. Okay. The countable intersection of open sets. Each of them is an open. So it is, but though 0 is not open, but it's a G delta set. It's a bigger family. F sigma set, G delta set. Like open set and closed set, you can see it is preserved by it is behave nicely with complementation. That means a subset is F sigma if and only if its complement is G delta. Okay. It is easy to show that a subset A of X is a G delta set if and only if X minus A is an F sigma set. Similarly, A is an F sigma set if and in X, if and only if X minus A is a G delta set. Okay. Now that I have given a note on that. Why is called F sigma G delta? Look here, sigma and delta. Sigma is usually topology and measure theory. It stands for countable union. Countable union. Okay. Whereas delta stands for countable intersection. In measure theory, also next semester you will be using this notation. Stands for that. Okay. So I have given examples of F sigma G delta set. Why I'm considering? Because these two types of sets plays big role in continuity. Okay. Here, just look at. You should do all these problems also. We consider the following functions in R. We have the usual topology generated by the usual distance. So you're taking this. When actually, when you do not mention any topology on R, and if you use topology, then it is understood you are using the topology generated by the usual distance. And that topology also called usual topology. Usual topology on R means the topology generated by this distance, usual distance. This is called usual distance. Now, okay. Now I have given example of the start with this example. So you take topological space, okay, like that. My question is, suppose you have a function, real valued function on a topological space. So this is your function. Here you have the topology. I am not saying what topology you have. Now the question is that I have to, now I know the definition of the continuity of a function between two topological spaces. So here f may be continuous at some points and may be discontinuous at some points. So I can take this t x belongs to x such that f is discontinuous at x. Look, this makes sense. The reason is d may be whole x, d may be phi also, but it is makes sense. So d is it's called the points of, d is the set of points of discontinuities of f. We say that the set of discontinuities, the set of discontinuities. Actually, you should write points of discontinuity. Then you write discontinuity. Points of discontinuity, set of points of discontinuity of the function f. So more precisely, it should be like df, because, but here I have taken f and f is fixed. Okay, so set of points of discontinuity of f. Now the question is that, can you, at your whims, that is, suppose I give you a set ax subset of x. Okay, and I say to give me a function f such that a is precisely d. Okay, this is the question. A, unless a behaves nicely, you may not have this. And what is that nice behavior? Okay, that we want to figure out. There must be some restriction on a, on not on any a you give me, and you can find this. Okay, that only on a you have the points of discontinuity, and points outside a it is discontinuous. It is continuous. That is not possible unless it has some property. That's why I have introduced f sigma g delta. Like here, I have taken x tau equal to this. Take, I'm considering, for example, the simplest case. So you have a function from here. Okay, right. Now I have given some examples. First of all, you assume that fx equal to 1 if x belongs to q, and equal to 0 if x belongs to p. P is the irrational. Look, this is discontinuous everywhere. Why? Because any rational, simplicity, to take x rational, then any rational point can be obtained as a sequence of this such that each xn belongs to p. Okay. Now look, if f is continuous, that we know that, then this will be always true in any topological space. If f is continuous and it's a continuous function, will always send convergent sequences to convergent sequence. Converse is not be true. That if a map sends convergent sequences to convergent sequence, whether it will be continuous. That I have given co-countable topology and uncountable set. But a continuous function always sends convergent sequences to convergent sequence. It follows from the definition of the convergent sequence. You can do it, prove it. Fxn goes to fx, but here anyway I am taking metric space, that's not a problem. Now xn is irrational, so it is 0. So everybody is 0 by the uniqueness limit of the convergent sequences in a metric space, so it should go to 0, but ax is rational, which is 1. So you are getting a contradiction. Similarly, if you choose this, so this is discontinuous everywhere. That means here d equal to 5. Okay, discontinuous everywhere. So nowhere it is continuous, so that actually d equal to x. Whereas if f is continuous everywhere, then d will be equal to 5. Okay, right. Like simple thing, if you take identity function, f equal to identity, that is fx equal to x. This is continuous everywhere. So discontinuous nowhere. That means d equal to 5 here for this function. Okay. Now I have given example, the problem number 2. This is very important. Okay, you should, I'm explaining that you should solve the problem. That page 77 of Aliprant's Barkinson. Look, what is this? Here, this what I have done. That A, you have a function from R to R. I have taken f0 equal to 1, then rational fx equal to 1 by n. Here rational you can write this way. I can take n positive, and also this means they are relatively prime to each other. Okay, that means only factor is common factor GCD is 1 and n greater than 0. That I can always do for rational numbers. When x is rational, then you take this representation, and if x is irrational, you take 0 if x is irrational. Here f0 is a rational number, but I have given it separately because so that you don't get confused on that. Okay, right? f0 equal to 1. Okay, we have taken that. So f0, so that you don't confuse with that. 0 is defined separately. X belongs to q minus 0. Okay, right? Otherwise it won't make sense. For non-zero irrational, it makes sense to talk about. So here I asked you to prove that here, because f is continuous at every, careful about my writing, at every irrational number. I wrote first rational number, then I realized it has to be irrational. So I put I here, irrational number. So f is discontinuous at every rational number. Okay. That means here you are getting what? D equal to, here you are getting D equal to
Q.
Okay. Now look here, whatever you got before also, here Q is a F sigma set. Okay. Before the example I was giving, look, I was having the whole set. Whole set is open, so this is also closed. Every closed set is F sigma. And when is phi? Phi is for any topological space, closed sets are, by definition, are F sigma. Okay, right? And similarly, open sets are G delta. So until now, the whatever example you saw, that the D has to be F sigma set. Okay, that exactly I want to prove that. It doesn't matter. That means you, any topological space, real valued function. I have taken the result. I want to prove it here. Okay, that I want to do through oscillation and that. Okay, so if you take a function, any function, I don't know what is the function, and any topological space here, the domain, and the D has to be an F sigma set, has to be. Okay, that I'm going to prove, but before that, look, what will be the consequences? Now suppose you have function now looks P. I told you by using Baire's category theorem, which I will teach you next. P is not an F sigma set. that actually proved by using Baird's category theorem. P is not an F sigma set. This is one of the first applications of Baird's category theorem. P is not an F sigma set. If P is not an F sigma set, we can't have a function like this. That's why I'm asking you to compare about the functions, the examples I've given in example 1 and 2. Like, you cannot have a function, you can't have a function such that which is discontinuous at each irrational and continuous at each rational. You can't have. And that is because I have proved already in F sigma set. And here I am saying it has to be an F sigma set. Okay, right. That I say, is it possible to find a function such that d equal to p? Of course, on R we are having this usual distance. Okay. Here, so this I am going to prove. Okay, this result. But before that, it's an interesting question that it is not exactly related, but still you should think about that. That suppose you have function here which is called additive function. That means fx plus fy. Like identity function is additive. Suppose you have an additive function. Okay, just think about it. I'm coming to that. I need to prove that. I will prove this. Okay. So before that, it's a food for thinking, and that you are doing linear algebra also. So now look here, since it is additive, we can prove that if f is continuous at a point, particularly f is continuous at 0, if and only if f is continuous at any other point. What we are saying, look, if you have an additive function, you can prove. I do not know continuity. I can prove that. That's not difficult. If f is continuous at 0, then f has to be continuous at any other point. That what does it mean? You just take epsilon delta definition. That will give you. That means if f is discontinuous, it will have to be discontinuous at each point. That means if f is discontinuous here, if f is discontinuous, then d has to be whole R. समझ गया? Either d has to be R or d has to be phi. No other choice for this function. Okay, this is possible, but still look here. F sigma set. Then any topological space x and phi, they are closed set, so they are F sigma set. So these are F sigma sets. So it is consistent with the theorem. Now what I am saying, can you prove that does there exist such a function which is continuous? That means continuous everywhere. Does there exist a function, continuous function, which is, first suppose,
Yes,
I'm
sir.
just going a little bit, f is continuous. So you have this first thing, fx plus fx. So suppose this is continuous. If it is continuous, you can prove that fx has to be equal to f0 into x. I think this is. I think it is f0, but in YAL it has to be fx equal to alpha x. There will be some alpha. There exists alpha constant such that for all x belongs to x. That means f has to be a multiple of the identity function. Understand? The identity function, if f is continuous. This much you can prove. This is not difficult. This is not, in fact, how will you prove this one? In fact, let me tell you this, though it is not written here. First you show for integer you have it, positive integer. Oh, sorry, this is not f0. This should be Now I got it. This should be
F1.
yes, you
F1.
are right. This is F1. M F1. When M is a positive integer. That is okay. And then you go for this, you can prove from the additive, you can prove that f of minus fx equal to minus fx. समझ गया? Okay. Because f0 equal to 0. Because 0 plus 0, f0, f0 plus f0, f0 equal to 0. So f minus f equal to minus fx. So m is if it's a negative integer, then still you have this. If m is a negative integer. Okay. By using this and this, then you can prove that fq, q f1, if q is rational. Then you'll have to take this q equal to m by n, just now I did. Of course, q not equal to 0 and m n relatively prime. It means that their common factor, highest common factor is 1 and n greater than 0. Okay. To prove this qmn, so you'll have to take m equal to nq. समझ गया? So fm will be fn q. But it is additive, so this will be n fq. N is greater than 0. N fq. समझ गया? But fm that already got equal to m. It is an integer. So fq equal to
M by N.
fm equal to m into f1. Sorry. M by n f1. So q f1. Okay. Now you'll have to jump to irrationals. How to do that? Okay. Here use the continuity. By continuity, because any irrational numbers can be obtained at the limit of a sequence of rational numbers. So use that, then you will get that. That means you will get fx equal to this one. Okay. This you will get. That means it should be a multiple of identity. Okay. If it is continuous, that you will get. Okay. That you will get if it is continuous. Okay. Well, well, fine. So that, well, if I give you such a function, then obviously you will have this additive. You can say, okay, I have got a function. That is fine. But I have said here, at which points the far f is discontinuous. This last question seems innocuous. Here you are starting with a function like this, but suppose I have given other additive function that you can say what is the existence of that. That means what I am saying, this question, look, that you now, so I have given you an existence of a function which is additive and continuous. But here what I am doing, you have only this information. Okay. Right. You have got a lot of information, but though not complete information. It is additive, and you will, what will be D? Well, you have already got D will be either R or phi. But if D equal to R is phi, then it's fine. That means everywhere it is continuous. And if everywhere it is continuous, then you got that fx has to be equal to x f1. Okay. Now look, that means there are many functions. F1 you can choose. You have the advantage here. You have the freedom to choose F1. So F1 can be any real number. That means any. That means you have uncountable choices. That are choices you have. That means at least you have that. If you change F1, you will get a different function. So that means at least uncountable choices you have. So uncountably many continuous functions you have. But what about the discontinuous functions? Okay. how to figure out what will be the discontinuous functions. This is the simple thing. Here I am telling you, I said the last question seems innocuous. Innocuous means harmless, but it is not exactly harmless. Okay. Here, in order to prove it, that what kind of discontinuous functions you may have, that is to have complete information. Look, you are doing linear algebra. Here R, you need to is the fact, R over Q, Q is a field, is a vector space. Okay. And every vector space has a basis. Here you use John's lemma. Every vector space has a basis. Basis or base, whatever you call it. So that R over Q has a basis. And that basis has to be uncountable. That means R over Q has a basis. And it has to be uncountable. Why? I have given you a problem, you proved, same way you proved that set of algebraic numbers is countable infinite, right? If B is countable, that for finite you can easily check out on that. Even if you check countable infinite. If B is countable, then since Q is countable, the way you have proved the set of algebraic numbers is countable, you can prove that, then R has to be countable. Okay. So that means a contradiction you are getting. So it has to be uncountable. By using this fact, you can attack this thing. That what will happen if you have the discontinuous function. You can have complete information. Okay. So that what I am trying to hammer to you, that it may not be very simple. Simple functions sometimes they look simple, but they are not that simple. Particularly even if you are taking real valued functions on a real variable, it may not be that simple. Okay. So actually oscillation helps to a large extent, not fully on that. So that what will be the oscillation? So I have defined in page 139. Okay. Look, page 139, I have defined the oscillations. This is oscillation of f at x, the notation. But in order to do this, so your x you are picking up and keeping it fixed. X you are picking up and keeping it fixed. Then you do have this nx. This is called the all the neighborhoods, the family of all neighborhoods of x in that topological spaces. All neighborhoods of x you should mean, that means all the open sets containing x. All the open sets in x containing this. It's called neighborhood system containing x. Okay. This I need for just notation of that. Okay. Now look, so that you have you take a neighborhood V here. Okay. I have defined, I took trouble in defining and that supremum infimum. I have given you the problems in minor, supremum infimum. But again I am telling you, your performance is not that bad in minor. The averages came around I think 15.5. That's what Dhiraj is saying. So it is 40% of that. But be careful. People who got below 10, they should be careful. Okay. And if you are aiming for A or A minus, particularly A, you should have got more than 32. So that if you got, I think, better than 30, I think 2 students. I think. But if you want to have a better grade than that, you should work harder. Okay, right? So that the performance is not bad in Jan, because reason is the first course like that probably you are facing. You have not undergraduate, you have not been taught like that. But in MSc you will face many such cases, courses of that. Okay, so it's not, even if you got 20, around 20, it's not bad, I'm telling you. As a first course, it's not bad. Okay, right? But you should work harder. Now, look, if you have V, that means V is a neighborhood of X. Now look, then FV is a subset of R, but R I have taken the metric space. So diameter of FV, it makes sense. Look, diameter I have defined only in a metric space, but here I am taking the diameter of the image. That means it is going to the range. Range is the real value. That's why I have taken that. If you are more enterprising, you could see that what I have defined, you could take a metric space here. It's about the range. You could replace this thing by another metric space. Diameter of FB. Okay. Now you take infimum. The diameter of FB by definition should be this. Diameter of FB. So basically distance between all these points here and their supremum. That means here Fz minus Fy all Zy belongs to Fv. Okay. So this is the definition of diameter. So actually Zy is the domain. So Zy should belong to V. Actually first what should be, I should have, so I can take this thing. Real number you have taken that. R1, R minus S, RS belongs to FV. Okay, that's actually should be this. But then RS we are taking as RFZ, S F1. Okay, so diameter of FB. Now for continuity of birth, I told you what is the intuitive idea of continuity. The closed points in the domain should be closed there. So diameter I should have as small as possible. That exactly I have given for the oscillation. That oscillation I am defining so that oscillation of that is called the oscillation of F at X equal to infimum, all this diameter of Fv. But of course it is, I am considering the continuity of that. So V is a neighborhood of X. That's why I have taken this neighborhood. That is over all the neighborhoods of X, you take the infimum of all this. That is called the oscillation. Look, each diameter is greater than equal to 0, so that it has to be greater than equal to 0. Got it? Okay. Now the question is that when it is 0. Okay, and that I have left an exercise with for you, so that oscillation is 0 if and only if F is continuous at X. Okay, that is theorem 3.4. This is an exercise for you, that omega Fx is 0 if and only if F is continuous at X. Look, for a real valued function on a topological space, there is another characterization of continuity at a point. Here locally we are looking at the continuity, that omega oscillation is 0 if and only if F is continuous on that. And next thing we are going to prove that's this thing, that theorem 3.5. Okay, I'm going to prove it, but I'm going to take a few minutes break on that. I'll be back after 5-10 minutes. Okay, read it. Oscillation. Try to understand oscillation well. Okay. Hello, I am back. Hello? Are you listening to me?
Yes,
Hello?
sir.
Yes, sir.
Yes.
Okay. So let me finish this result. Okay. So that here. So D. So that means about this, because of this result, D, the discontinuous, will be X belongs to X such that F is discontinuous at X. Okay. So now look, that means by this, F is discontinuous at X if and only if omega F X greater than 0. So that means D equal to, I can write X belongs to omega Fx greater than 0. Now look, omega Fx greater than 0 means what? That here omega Fx greater than 0 if and only if there exists n belongs to n such that doesn't matter how small, I can choose n arbitrarily large. So there exists n. Okay. So that this will happen. So that we call Dn is this. X belongs to X. Look how I am trying to simplify the problem before trying to prove it. X belongs to X such that omega Fx greater than equal to 1. By now, if you get some intuition about open set, closed set, you'll understand that why I am taking greater than equal to 1 by n, not only greater than 1 by n. That way I could also take. You will see that why. Now Dn is this. So that D will be equal to what? D will be equal to union of Dn. Okay. Right? And I want to prove this is an F sigma set. That means countable union of closed sets. So it is countable union of Dn. So all I need to prove that each Dn is closed. I will be done. Each Dn is closed. And in order to prove closed, that's why I have taken this greater than equal to. Okay. Now look, Dn is closed. Look my statement of theorem 3.5. And I have given the reference where in the book in the early parentheses you'll find it. Let X tau be a topological space and Fx then the set is discontinuous. In particular, the set of points of continuity of F is the G delta set because complement of an F delta F sigma set is the G delta set. So the points of continuity will be a G delta set. Okay. So the Dn, now I want to prove that. So for proof, to show each Dn is closed in X tau. Look, I do not have any many tools in my hand. Dn is closed, you can prove two ways. Either you prove it is complement is open or you show that Dn bar equal to Dn. Okay, but Dn bar that is also would be a bit cumbersome. So I will prove that it will be easier that X minus Dn is open. Okay. In order to open, I will prove that any point here is an interior point. That means if you take this X minus Dn, I will be able to put a neighborhood here, okay, inside. That means an open set. So that X minus Dn will be open and Dn is closed. So that is the idea. But now it follows from the definition. Now look, I said X belongs to X minus Dn, that you have taken. x belongs to x minus dn. Look, what is dn? dn is omega fx greater than equal to 1 by n. So it means less than 1 by n. ठीक है ना? Okay. Omega fx less than 1 by n. But this means what? Look, go for the definition of that. Omega fx is in diameter of fv. V belongs to an x. So here you have omega fx. Here you have less than 1 by n. This is 1 by n. So that means you will get a neighborhood of x such that diameter of AP will be here, it will be less than 1 by n. So that by definition of this infimum, so that you get there exists a neighborhood of x such that diameter of AP less than 1 by n. Got it? Okay. Now V is open. That I already mentioned while defining topology on that. And x belongs to V. V is open, so V is a neighborhood for each of its points because V is open. So what I want to claim, I have got this. X belongs to V because V belongs to Nx. V, and this I want to prove. This is the question. This is the I have chosen. Okay, this I want to prove that Vx minus P. Well, you choose any A belongs to V. Now look, what will be omega Fa? Look, V is also neighborhood of A. So by definition of omega Fa, oscillation of F at A will be less than equal to the diameter of Fv. Look, V is not only a neighborhood of X, V is a neighborhood of A also. So by definition of this, I will get this. But diameter of Fb, I got less than 1 by n. So that I get this. But what is x minus gn? That is precisely this. All those points whose oscillation is less than 1 by n. So that A belongs to x minus dn. Look, I have chosen any A belongs to V and I have shown that this is this. So this is right. So you got each point of x minus dn is an interior point. So x minus dn is, समझ गया? So that dn is closed. So that T is an F sigma set. So if you take C, x belongs to x, F is continuous at x, then C is a G delta set. Well, I am just inviting you to try. I proved D is an F sigma set. Could you prove by using the same thing, arguments, oscillation and that? Because you remember that F is continuous at x if and only if omega fx is 0. So you can see that whether you can prove directly C is a G delta set. Okay, can you prove that? Okay, C is a G delta set. Just try it. Now I say it, go back to this, that exactly what thing I explained that. Okay, that about P irrationals cannot be, is not an F sigma set, and that already I talked about it. Okay, already I talked about it. So this is okay. So today I won't teach you much of this. I just want to explain that. I won't prove any result. I think you are also getting tired. I will explain that. Chapter 4 Bayes category theorem, I have written that. So this one is got But this is very important. Make sure that you also do that f is continuous at x if and only if omega fx is 0. You prove it. Okay. Try yourself. Then you ask Bhavna or Dhiraj. Okay. Right. Now look, I was talking about Bayes category theorem here. That exactly needed. So what kind of functions on the real line you can have? Bayes category theorem. Look, Bayes category theorem, again you should look at the definition. Nowhere dense set. Look, dense set, you know that. Okay, I am taking an X tau topological space. So A subset of X. A is called dense. A is called dense. Mode pixel dense in X if a bar equal to X. Where A is called nowhere dense. A is called nowhere dense. That means everywhere basically it is hollow. Basically hollow. It is called nowhere dense if interior of a bar equal to empty. That I told you, this is important. Like interior of Q is empty, but interior of Q bar is same as interior of R, which is R. So be careful about it. Okay. So nowhere dense. Okay. So that here I gave you that. And sum-are dense. Actually, I won't be using sum-are dense, but sum-are dense means if you have this, that it is non-empty. That is called sum-are dense. Okay. Now proposition 4.1, I have given basically the alternate equivalent characterizations of that. A is nowhere dense if and only if it follows from the definition. Actually, you don't right now need C, but you can prove that A and B, that A is nowhere dense basically in X if and only if X minus A bar is dense in X. Actually, I asked something related problem in minor. Counter example. So A is nowhere dense means that interior of A bar equal to phi if and only if right is X minus A bar is dense. So X minus A bar whole bar equal to okay, right. I think you should be able to do it. It's not difficult. Okay. So that here B implies C also is not difficult. I am not telling you that C implies A. It's a bit tricky. That you should try to see that. Okay. Right. And then I defined first category. Set of first category. It is if A can be a set, A is a set of first category. Everything in topological space you are doing. Like here you will see that why I talked about topological space instead of metric space. Here only we deal with open set, closed set. We do not need any metric D. Okay. The first category means if you have this, it can be there exists n, not for all n. There exists such that each n is nowhere dense. For all n. If you can have this, that is countable union of nowhere dense set. Countable union of nowhere dense sets. Okay. Look, Q Q is a set of first category because Q can be written as this. And here, each point is nowhere dense. Okay, so that Q is a set of first category. Okay, later on we'll see then P has to be a set of second category, but that will require Bayes category theorem. A set of second category. Second category, you will say what? If I already defined, but again I am telling you. First category, if it is countable union of nowhere dense set. If a set is not of first category, then it is called second category. Okay, there are only two categories. First category, second category. If it is not a set of first category, then it will be a set of second category. That means whether some set is a set of second category, you will have to go to the definition of first category. That means it can't be written as a countable union of nowhere dense set. That means second category means a second category of second category if A can never be written in that topological space, can never be written as a countable union of nowhere dense sets. Okay. That means if you have the information, suppose you have it, you are having this, suppose and you have the information that you have it is a set of second category. And at the same time, somehow you are getting this, that in functional often it happens. That you get this, that means can never be written as this. That means at least one n there which is not nowhere dense. That means there exists n not immediately conclude such that interior of a naught bar not equal to 5. That means somewhere dense. That means there exists some n naught such that a n naught has to be somewhere dense. Okay, that's the thing. Second category. Usually we use this way. Okay. So now there's a Bayes space in that definition. I'm not going to prove any result on that. Bayes space is that if every non-empty open subset, of course, empty set we do not consider on that. Okay, you can think of that. By definition, empty set will be set of first category or second category. Okay, that you can think of that. Okay, empty set should be what? Interior of phi bar. Phi itself is the closed set. So interior of phi is phi. So it is actually nowhere dense. So particularly set of first category. So empty set cannot be a set of second category. Okay. I said it's a Bayes space if every non-empty open subset is of second category in X. Bayes space. Okay. That's the definition. Every open subset of X, so that means it is stronger than loop. If X tau is a Bayes space, if every non-empty open subset, non-empty open, okay, subset of X, open I underlined, of X is of second category in X. That means in X tau. Particularly X itself is a non-empty open set. So if you have it as a Bayes space, then X is itself of second category in X or in itself. In itself means in X. So often we use that fact. If X is a Bayes space, then X is of second category. Okay. Well, let me tell you that theorem 4.2 actually is a very basic theorem while dealing with Bayes space. Okay, I'm not going to prove it. Okay, you should read the proof, but I will be using this thing. Okay, I will be using this thing so that theorem 4.2 I have given 4 equivalent conditions of the Bayes space. But usually I made a comment. Some people prefer B. without going to open set and that, because it says countable intersection of dense open sets, intersection of any sequence. That means countable intersection of dense open sets is again dense in X. Many people prefer to use this itself as a definition of Baird space. But this theorem shows this thing and this thing are equivalent. Okay. In fact, I am telling you, topologists they prefer A as the definition of Baird space, where analysts they prefer B as the definition of Baird space. So that you should look at B, the intersection of any sequence of dense open sets again. That means if you have UN, a family of open sets, suppose you have UN, each UN is open, whenever UN open and each UN is dense. Its meaning is then this, look, I'm not saying it is open, because countable intersection open set need not be open. But what I'm saying, this will be dense. Okay. That's the equivalent characterization of Baird space. Actually, often you use it to prove something is a Baird space, right? We'll prove this. Actually, we'll prove every complete metric space is a Baird space. Every complete metric space is a Baird space. So usually we prove this. Why we prove this? We use this. Okay, look. Actually, big result is this. Every complete metric space is a Baird space. This is a big result. Okay. And in order to prove this, actually we use B. And to use B, why use B? Here you use Cantor's intersection theorem. I told you that Cantor's intersection theorem is important in the sense in order to prove many big results, important results, we need this thing as a tool. It's a very powerful tool, Cantor's intersection theorem. Look, Cantor's intersection theorem, we need a complete metric space. Okay, so because of the moment to have this, I can think of that using this. So that by using, we prove that every complete metric space is a Baird space. And remember that if you have this, then this is a Baird space. And by using this, just now I was using that, you have proved that this is not an F sigma set by using this. The fact this is the Baird space, and so and P is not an F sigma set, and that gives you many restrictions on your continuous functions in that. Okay, that's what I was explaining to you. Okay, so that I will prove this by using this. So that means I will prove this theorem. I am not going to prove it, that of course not today and that, but I will prove, okay, this theorem. Look, of course I am making many lot of comments. The theorem 4.3, it is page 146. Okay, I am going to finish my lecture, but I want to tell you one thing. When in analysis or topology, to prove any result on that, what is the important things? Like later on, like Baird's category theorem is one. What is the importance of that? I'll tell you. After I finish Baird's category theorem, then I will teach you compactness. And I won't get much time, but I will give an introduction about connectedness. But next semester I will teach you connectedness in detail. Connectedness, I talked about cover before. So here basically whether every open cover has a finite subcover. And connectedness means, look, X and phi are both closed and open. So given a topological space, the question is that does there exist a third set, third subset, that means which is neither X nor phi, which is both closed and open? That's the question. Now, why I am taking these things, three things: Baird's category theorem, compactness, connectedness. Any result, any good result, either in analysis, and by analysis I mean both real analysis, function analysis, even complex analysis, and topology. In its proof, it must use one of these things. If you say, no, I have found some result that where they don't use it. If they don't use it, they are using some other result to prove it, which that result uses one of them. So that Baird's category theorem, compactness, connectedness, on these things, the pillars, the whole analysis and topology, they are built up. Okay, so if you have a good result, you should find out after you have studied all these things that whether I am using one of these results or not, directly or indirectly. Sometimes you may not use a result directly, but you must be using indirectly. Indirectly means you must be using some result. That result uses in its proof one of them. Okay, that's what I'm saying. If you do not use this thing, only one of them, that may be a very small result. That's not a very powerful result, not a strong result. That you should keep in mind. If you are interested in math, in analysis, topology, and that, even measure theory, you will see that also. Okay, that where you will have this. Compactness plays a big role there. Okay, of course, higher measure theory and that. So that I will take before your mid-semester break, so-called, and Dasera, tomorrow I will take the class, okay? The same time. Okay, I may be 5 minutes late on that. I don't know, when I try to log in, my laptop works a bit slowly on that. Probably some other people, they also log into MS Team. So tomorrow I will be taking the class, okay? And tomorrow my aim is to finish this note. Actually, I will prove this result, what I told you, that every complete metric space is a Baird space. Okay. Right now in Baird's category theorem, you just need that result. Every complete metric space is a Baird space. Okay, that will be good enough. So next semester probably I will teach something more. Okay, bye. Hello? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
ठीक है, tomorrow I will see.
Okay, sir. Bye, sir.